Oh, okay. Thanks also to the organizers for inviting me. It's always nice to come and visit in Saclay. So I'm going to talk about work that's from two papers, both of which are with Ed Copeland and Pete Millington in Nottingham. And although I gave quite a general title, what I'm actually going to talk about here is just symmetron models, symmetron screening. So to give you a rough outline of how the next half hour is going to go, I'm going to remind you how the symmetron screening mechanism works. And then I'm going to show you that it's possible to construct this screening mechanism in a radiatively stable way. And then we're going to go and talk about what effects this scalar field could have on galactic dynamics. Okay. So this, at least in this form, the symmetron screening model is due to Justin Curry and Kurt Hinterbeckler. And the idea is that you have a canonical scalar field. It has some potential and some coupling to matter in the way that we're used to from Horndeski. And in particular, we have a phi to the 4 term in the potential and an tachyonic mass term. And the coupling to matter goes like phi squared, not phi. So there's a phi goes to minus phi symmetry in the model, and hence the name symmetron. And the point is that this gives you an effective potential where the effective mass of the field depends on whatever you think the local energy density is, at least in non-relativistic spacetimes. And there's a spontaneous symmetry breaking transition as you lower the local energy density. So to show you that in pictures, we're going from high density on the left to low density on the right. And as you lower the density, the field which wanted to sit at the origin in the high density region picks up some non-trivial VEV as you lower the density. And the reason this works as a screening mechanism is really because we chose this coupling to matter here that was phi squared, not just phi. So there's an effective coupling constant here in the force mediated by the scalar field, which is proportional to the VEV of the scalar. So in high density regions where the field wants to sit at the origin, phi is 0 and there's no force. So you either don't feel a force or you don't source a fifth force. Okay. Now, this is nice, but obviously what I've done here is I've picked some very specific set of terms from Horndeski or from our EFT of dark energy. And if we want to do that, ideally we would like to have some reason that says that it's sensible to pick those terms and ignore the others. And in particular, that the others are not then going to be generated by quantum corrections. In particular, this is true of all of the things that we study in screening because we're intrinsically relying on nonlinearities, and these are non-renormalizable operators. Now we have some nice examples of this already, in particular Galilean and DBI, where you have a symmetry that tells you that sometimes you want to keep and some you can safely ignore. And one of the things that we wanted to ask was, well, these two theories that we know, those are both theories that screen through the Weinstein mechanism and have non-minimal kinetic terms. Is it possible to come up with a theory which would be radiatively stable but screens through some potential nonlinearity, so nonlinearities in phi rather than derivatives of phi? And of course, if you're worried about radiative stability, you don't only have to worry about self-interactions of your scalar field, but also about the effects that come from the fact that you want to couple to matter. And if this is our scalar field propagating, maybe there's some loop of some standard model thing here, which gives our scalar a much larger mass than we would want. Okay. So the idea of putting these two things that I've just told you together, the symmetron model with this spontaneous symmetry breaking mechanism and radiative stability, this has a long history, right? Doing spontaneous symmetry breaking in a radiatively stable way goes back at least to Coleman. And we're going to do something very similar to that here. But the point is, if you're just doing this with one scalar field, the Coleman-Weinberg mechanism, at least in the simplest model, you have one scalar field. You start with a scale invariant model, so just with the quartic self-interaction of the scalar field. And then you compute the one-loop corrections to the potential, and indeed you get exactly this spontaneous symmetry breaking mechanism. But the point there is that if you wanted to live in the broken phase, exactly at that point, you know that the higher order loop corrections also become important. So you can't trust your one loop potential exactly where you want to live to have this to work. So what we have here is an extension of that where we go from one scalar field to two scalar fields. And the advantage of that is, so just to go through, we have some non-minimal coupling to the Ricci scalar, Lagrangian for our two scalar fields, phi and x here, and then some other matter fields kicking around in the model. And our scalar fields, Lagrangian is completely scale invariant. It's not quite symmetric in phi and x at this point. Just for calculational simplicity, you could absolutely add a phi to the 4 term here as well, but it just makes the algebra worse. And the advantage compared to just doing this with one scalar field is that we have now two coupling constants instead of one, two-dimensional constants instead of one. And that really is at the heart of the fact that we're going to be able to do spontaneous symmetry breaking at one loop in the potential whilst keeping the higher order loop corrections under control. Okay, so we're going to minimally couple again to gravity in the same way that we talked about before through a phi squared term. And yeah, as we said, at tree level, this is a massless theory with no scales. So you do the standard thing, you compute the one loop corrections to your potential, and you find that this scale invariant property is broken, as you would expect. And this is the one loop potential that we get for the perturbations around the background, so for phi and chi. And what we find is that in one direction the fields are stabilized, and in the other, so chi then is stabilized at 0, and in the other direction we get exactly this kind of spontaneous symmetry breaking potential that we were looking for. Just to say how we've done the calculation, we treated gravity as a classical source, so there are no graviton loops in this calculation. And we've assumed that the background, the space-time background was Minkowski, and the background field configurations were constant. So we have neglected any gradient effects that might be there.
So the problem with that is that because you're not in Einstein frame, there is a mixing with gravity. And the main source of non-regular gravity is actually that mixing operator. Because put your theory back in Einstein frame, and you see the potentials are non-normal.
Right. So I think this is something. So this is something that we thought about. But obviously, if you move to the Einstein frame, then you're quantizing slightly different combinations of the scalar and the graviton field.
Yeah,
so
that's the right one because there's no mixing. So that would be the one to get the right answer.
I'm not sure I agree necessarily with that.
No, absolutely. I mean, you should quantize everything.
Right.
But the Einstein frame is the one that, because you remove the mixing, then there's a clear decoupling between the loops from the graviton and the loops from the scalar.
Okay, but I only want to talk about this as a low, so I don't ever want to go anywhere near the Planck scale. So I only want to talk about this at low energies where I don't think, so this is the same thing that you would do for the Higgs, right? Where
it's the same crime that Higgs inflation people make because they argue that the Lagrangians renormalizable, but it's not because they forgot to include the mixing piece. So there's a large,
okay.
part is actually larger than you expect because of the mixing.
Okay, maybe we can talk about that because I think we did at least some estimates where we convinced ourselves that the mixing with gravity was a. It's just a little bit harder to do the calculation. I mean, we could. So we did. We tried to do both and convinced ourselves that this was a simpler way to present the calculation, and that at the end of the day the corrections were small. If there's something that we've missed, maybe we can talk afterwards. Okay. Okay, so this is what we've done, and this is the potential that we get. So if we now just slice through in the interesting direction where we have the spontaneous symmetry breaking, This is the one loop potential that we have. And now if you think about how this how the spontaneous symmetry breaking happens as you go from high density regimes to low density regimes. In high density, we restore the symmetry again, and we live here. And in low density, as you lower the density, you exactly go through this transition again. Because it's not quite the same potential that we had before, you have this sort of slightly more interesting regime as you go through the spontaneous symmetry breaking, where you have one potential with three minima. But in practice, the phenomenology of this model is going to be almost identical to the one that we're used to for the symmetron. So then you can ask, okay, what is the parameter space for this model, and when is it radiatively stable? So these are the two conditions we have. One, to ensure that the scalar loops remain, the higher order scalar loops remain small, and one, to ensure that the standard model corrections are small. So this is the Higgs vev. The most important corrections are coming from the mixing with the Higgs. So this is the parameter space we have for our model. So this is the coupling to matter on the horizontal axis, and the vev of the field in the spontaneous symmetry broken minimum normalized to the Planck scale on the vertical axis. And so how you should read this this plot is you pick your favorite value of lambda, the quartic self-interaction. So if you like lambda is 1, you look at this line. If you like lambda is 10 to the minus 10, you look at this one. And if you want to be in the symmetry broken minimum in the universe today, you want to be above that line, above and to the right of that line. Okay. The gray region in the corner up here is the region of parameter space that's ruled out by PPN. The blue region up here is the region in which the higher order loop corrections become important. So this is where we don't trust the theory. So you want to live below the blue line and below the gray line. And then if you wanted to insist that your fifth force was stronger than gravity in the cosmological vacuum today, you live in this white kind of trapezoid region in the middle. Okay? And what you have on the right-hand side, right-hand vertical axis, is this self-interaction parameter times the Compton wavelength of your field in centimeters. Okay? So this is a radiatively stable version, so we can trust our scalar potential here and know that the higher order loop corrections are under control. Unfortunately, for doing dark energy or something with this model, we can't quite push the Compton wavelength up to cosmological scales with the version that I've presented here. In practice, it's really this, the mixing with the Higgs that kills you, although it's possible that you could extend the model with something like a Higgs portal term and cancel this out. But that's not something that we've worked out yet. But there are still interesting regions in this parameter space. So for example, if you lived around here, you would have a strong first order phase transition at around a TeV, so potentially interesting for something like LISA in terms of producing gravitational waves. And you have a Compton wavelength for your field of the order of centimeters, so also potentially interesting for laboratory searches for fifth forces. Okay. So now for the second part of the talk, I'm going to go back to the standard symmetron model just because it's a bit easier to compute with. But as I said, actually in practice, the phenomenology of the two things are the same. And talk about what effect this could have on the dynamics, on the internal dynamics of galaxies. So we're all obviously very used to this picture, right? That the rotation curves of galaxies imply that there's the baryonic matter is not enough to explain the rotation curves. And what we wanted to ask was, if we are interested in light cosmological fields that give you fifth forces, how much of an effect does that have, or could that have, on the rotation curves of galaxies? So the first, most kind of simple thing that we did, or that you could do, is just say, well, okay, let's assume there's no dark matter is it possible that we could do this with just, we could explain just the rotation curves with just a symmetron fifth force. So we took a kind of standard density profile for a typical galaxy and some typical profile for the rotation curve and asked what form of the scalar field profile would you have to have in order to explain the rotation curves, and got something like this. So this is the radial distance from the center of the galaxy as a function of the galaxy scale length, and the scalar field profile normalized to, this is essentially the VEV in the cosmological vacuum. Oh, okay. That doesn't look that weird. That looks like the sort of thing that you might typically expect to arise. So then we went, okay, but this was just some idealized analytical calculation. What actually happens if you try and confront this with the data? So we looked at the Spark data set, which Anish also introduced on Monday. So what is shown here, so the data points are again the velocity, the rotational velocity of the galaxy as a function of the radius in kiloparsecs. These are just for 3 example galaxies, just for the moment. The blue line is how much rotational velocity you would predict just from looking at the baryonic component in the galaxy, so adding together all of the stars and all of the gas. And obviously, as you would expect, the baryonic contribution is less than you need to explain the rotation curves. But then we put in our symmetron fifth force as well, and that, with this particular choice of parameters, is the orange curve that you see here. And adding the orange curve and the blue curve gives you the black curves. Okay, and this is, I think, I should have checked this. I think a few percent, or maybe 10% error bar around our symmetron parameter, so the shaded region. Okay. So again, we were surprised at how well this works. And in particular, it allows you, because the dynamics of the rotation curves are coming directly from the baryons, it allows you to nicely explain these kind of apparent correlations between features in the rotation curves and features in the density profile. Yeah, sure. So maybe this is not the best example to point at, but sorry? Here. Yeah. Okay. So it's better than we expected. It's not perfect, obviously. It doesn't go through all the points. But this is just for 3 example galaxies. So okay, hang on. I'm going to come to the whole data set in a minute. For these 3 example galaxies, just to show you again, these are the forms of the symmetron profiles that we get. Now actually extended much further out, I think a factor of 10 times. Yeah, okay. So this is, for example, 25 kiloparsecs where we have the data, and now 250 kiloparsecs, just to show you the form of the symmetron field profiles. And again, so this is just to show you that nothing weird is happening, right? These are all perfectly smooth, kind of kink-like solutions. We have, at the moment, only done this for one choice of the parameters, which turns out to work. We would like to do something much better than that, to scan over the parameter space. But the problem is that the differential equations are very stiff. And precisely by pushing down this coupling constant m, which is what we would like to do, takes us further into this stiff regime. So at the moment, all I can say is that these are examples of parameters that do this. So this is the full Spark data set. So they have rotation curves and baryonic profiles for 153 galaxies. And one of the things that they've done with this data, which you may have heard about last year, was to look for correlations between the acceleration, the observed acceleration of the stars as they orbit the galaxy, and what you would predict from the baryonic physics. Okay. So you can see that there's some potentially nice correlation here, which is explained in the original paper by this fitting function. And sorry, there was something else I was going to say, but I've forgotten, so it's okay. Carry on. Yeah, so this is, if you like, a generalization of the baryonic Tully-Fisher relation, where the observed dynamics of the galaxy seem to be tightly correlated with the baryonic physics, when you wouldn't necessarily a priori predict that to be the case if you have a lot of dark matter in your model, particularly on the edges of the galaxy. Okay. That said, there was almost immediately afterwards a paper by groups of people who simulate dark matter distributions in galaxies, and they claim by putting in the baryonic feedback that they can indeed get this relation. So this is not to say that you can't do this with dark matter, just that it's potentially an intriguing correlation. Anyway, so this is what we get trying to do the same thing with our symmetron model. So this is again the acceleration just from the baryons, and this is now the total acceleration that we would predict if you put in a symmetron fifth force and no dark matter. So the scatter here maybe looks a little bit larger than what was on the previous slide, but in fact this is just because they've binned their data and we haven't binned it by galaxy. And this is the correlation between the total acceleration that we predict and the observed acceleration in these galaxies. Okay. So what do I want you to take away from this? Because clearly I have not done enough here to suggest that this is a viable alternative to dark matter. The first thing I think is just that it's interesting that you can do this just with a canonical scalar field. So this is a really boring scalar field model, right? It's just got a mass, cortex self-interaction, and a coupling to matter. There is nothing really kind of dramatically unusual going on here. And I think the reason why the symmetron can do this, where other models have struggled, is actually because of the phi squared coupling to matter. The fact that the fifth force depends both on the field and the gradients of the field seems to help us fit over the whole extent of the galaxy. Also, we can explain not only the rotation curves but also the stability of the disk galaxies, which dark matter also helps you to do. If we wanted to go further and suggest that maybe this, to see how far you can go with this kind of fifth force model, obviously then we need to look at the other data sets. I think it's clear that you can't, just with this model alone, you can't explain the lensing, because this is a conformally coupled scalar field, so it doesn't have strong effects on photons. But following, sorry, I should have given a reference here, following a paper by Justin Curry, we think that if you add in an additional disformally coupled scalar, then potentially you might be able to explain the lensing and the cosmological background evolution. Obviously, if you want to do the CMV, there's much more work to be done there. Okay. But I think just from what we have here, I think there are sort of two things that I wanted to say, which is that, you know, if we are really serious about thinking about fifth forces on cosmological scales, if they're present on galactic scales as well, we may be significantly overestimating the local dark matter abundances, not by kind of sort of tiny numerical factors, but by significant amounts. And maybe this has implications for how much dark matter we think there is locally. And also, I think it has implications for models of light dark matter, where people are thinking about dark matter being a light scalar field, or something like, which goes by the name of fuzzy dark matter, where at the moment people are not thinking about the fact that that scalar could be non-minimally coupled to gravity, and so not thinking about whether there are also fifth forces present in those models. Okay. So just to sum up, I've tried to convince you that the symmetron model can be constructed in a radiatively stable way, that symmetron fifth forces on their own without any dark matter can explain galaxy rotation curves and stability, and also they give you a nice explanation for correlations between the observed dynamics of the galaxy and and the baryonic components. Thank you.
Thank you.
So these models that you presented obviously don't screen the solar system, right?
Okay, sorry, yes, thank you, I should have said this. So actually the value, this particular value of this coupling doesn't screen. It is in tension with the ppm bounds. That is exactly why we want to push to slightly lower values of m, where the numerics get stiff, because we think actually what the profiles are sensitive are the ratio of mu and m. So we should be able to push m down to be compatible with the ppm bounds and still be able to do this, but I don't have those numerics.
I don't think so, because as your rotation curves show, right, you need a 50% enhancement, roughly, of your rotation velocity at the position of the sun. And so if you want to explain that with modified gravity, then that means the sun cannot be screened in the chameleon sense, because the chameleon screen only depends on the radius, how far you are, right? So because it only depends on the potential. So I don't see how you can get rotation curves and screening with a chameleon or symmetron type model.
Right. So people always say this, that that chameleon or symmetron screening only depends on the local Newtonian potential, which I think is not quite true, because actually it's that.
In a strictly symmetric setup, it is true.
Well, okay, so there are two things that, so one of which is not what I'm talking about, which is the lab test, where it's absolutely not true, because then you can isolate your system from the cosmological background. But in this case, so this is the smoothed background configuration. Obviously, when you are looking at kind of stars on top of this background, there are going to be perturbations on this. And I mean, okay, it still remains, I don't have a conclusive proof that we can do this, but it's something that we want to work out. I think it should be possible, just precisely because what is driving the rotation curves is the ratio of these parameters, and I think the screening of the solar system depends on a slightly different combination.
So let me just add one more quick remark, because let's forget about the Milky Way. There's, of course, also dwarf galaxies,
Sure.
which are completely dark matter dominated.
Right.
And we know from distance indicators that the stars in there would have to be screened. So that case will be even much harder, I think, to get to work.
Right, it's true. I hope I made it clear that I'm not trying to sell this as an alternative to dark matter at the moment, but absolutely you can ask those questions. So an advantage that we have here over something like MOND is that we're not putting in hard acceleration scales here. The symmetron is responding to what you think the local density of the baryons is. In principle, you have more of a hope that you can extend this to a wider range of systems and still explain what you're seeing. But absolutely, pressure-supported systems or really diffuse systems, we haven't looked at here. I can't say anything.
My question was about what you just said about the acceleration scale. If you go to the slide, the next one, that one. If you look at that curve, I mean, it has two limits, and in between you have an acceleration scale.
Sure.
And that comes from the data.
Yeah.
So the data has an acceleration scale embedded. The question is, can you somehow from a symmetron or chameleon, whatever, get an acceleration scale?
So we don't have one hard fixed acceleration scale that works for everything, precisely because the symmetron is responding to what you think the local density is. But I think that's a feature, not a bug, of the model, because it actually allows us to do better than something like MOND would do in this case.
More questions?
If you wanted to consider the lensing, why don't you just put the coupling to photons in, because it's going to be generated by the conformal anomaly anyway, as you know.
Yeah.
And the second question I have...
Okay.
Okay, no, go ahead
Do you
and
want
answer that one.
I don't mind. Okay, so the problem with that is that you only mix one component of the photon with the scalar fields, and so you would lens one component of the photon and not the other. So just with adding in that axion-like term, you can do it. In fact, even just adding in a disformal coupling for the same scalar field doesn't work. It doesn't do enough either, just because the scalar field profiles are so shallow that it doesn't lens the photons enough.
I mean, also on, I think, an extension, or perhaps not quite an extension of Fabian's thing, you wouldn't get clumping of the dark matter halos, would you? I don't know.
Okay, that is well beyond what we've done. I don't have any good sense of the evolution of this.
So you mentioned as a caveat right at the end the CMB, but I mean, even in principle, how do you think this might work? It's a CS equals to 1 scalar field, right? So
yeah. So I think you could imagine, getting the cosmological background evolution by adding in a second scalar field which doesn't clump, but which behaves like cold dark matter on the background. And that is exactly the thing that Justin does in his version of trying to do this. Exactly. Whether that is enough to actually fit all the CLs is a different question.
More questions? No? Okay, thanks a lot then.